What's up, everybody? My name is Jason Dobies. I'm a developer advocate at Red Hat, and today I'm here to talk to you about pretty much movies. Let's do some administrative stuff first. So this talk was designed to be a bit interactive with the audience. It's a very fun talk to do in person. I get people involved. I get people shouting things out. I throw t-shirts at them. Unfortunately, the world we live in today, we're doing this from my office in my house. But that's okay. The way I understand things, we're going to be watching this, so I have to listen to my own voice, which is always uncomfortable to hear. But we all can hang out in a chat room as this is going on. So I invite all of you to be very vocal in there. Let's have some fun with it. Let's play around with some of the questions I ask and just generally keep it as lively as we can, which is even more important given the current state of things. So with that said, I sat down to write a talk, and I turned on my TV, and I'm flipping through the channels, and I see Sean Astin on the screen. I'm like, this is great. He's a geek icon. He was Bob in Stranger Things. He was Samwise Gamgee in Lord of the Rings. He was Mikey in Goonies. I'm like, this is going to be great. It's going to put me in a nice nerdy mood to write a talk. No, the movie's about football, which I don't particularly care about. And the name of the movie is Rudy. It's about Sean Astin is this kid who wants nothing more than to play Notre Dame football. But he's constantly told he's too small, he's too skinny, he'll never do it, and he pushes. And the whole movie is about him getting a spot on the team. And then near the end of it, he finally goes to play. And the coach is like, are you ready? And he's like, I've been ready for this my whole life. And then the rest of his team starts chanting, Rudy, Rudy. And then the fans in the stadium, just Rudy, Rudy. And me, I don't care about football. I'm in my basement and suddenly I have a Notre Dame pennant. And I'm like, Rudy, Rudy. And the movie, it just absorbed me. And I realized that sports people get all of the cool movies. I'm not really a sports guy. I'm a computer guy. And we get stuck with this. This is a fairly common or very popular example of one of the worst things you've ever seen on television in terms of describing what us computer nerds do for a living. And it got me thinking, sports guys get all the cool movies. We don't get that. So I have a couple of examples of computer movies before we get into the talk details of where they've done us some injustice, either particularly technically wrong or particularly corny, and you'll get where I'm going with this as we get started. First, apologies for spoilers now. I won't really go too into storylines here, but all of the movies came out before 2001, so I think the statute of limitations on getting them spoiled is well past. And honestly, these are fairly solid hacker trope movies that if you haven't seen by now, it's on you that you're getting them spoiled because you probably should have seen them. So let's start with my first example here, Exhibit A. This is a screenshot from one movie in particular that I'm thinking about. And in this scene, she's navigating a Unix file system. And apparently this is what Hollywood thinks we do, that we spend our time with these grand flyovers, and when we find what we want, the file is selected with a cool spotlight, and this is obviously way more efficient than all of the command lines that we've grown to love. And this is what Hollywood thinks we do. This is what our loved ones who don't really understand what we do for a living, they're like, oh yeah, they're doing their flyovers and their cool 3D UIs. This is a particular old movie on top of this, and it's funny to look in 2020 that we're still sitting in a command line when we're most comfortable. This movie birthed an amazing quote. This is actually the name of a subreddit that does nothing but highlight these types of movie inconsistencies. If you've never checked out the subreddit, it's actually hilarious, but our hacker here, she sits down at the computer and she sees this graphical flyover and she goes, it's a Unix system. I know this. Absolutely amazing, comically hilarious scene. So again, normally live, I would have the audience shout out to me what the name of the movie was. Hopefully, everyone is pretty verbal in chat right now and have been shouting it out and laughing at it the whole time. But in case for some reason you didn't pick up on it, the movie is Jurassic Park. Not specifically speaking a computer movie, but close enough in the technology realm that I don't feel bad ripping on its representation of computers. Interesting fact about it, though, in that scene, we saw it was the young girl, the daughter, who was the computer hacker. In the book that the movie was based off of, and I really hope no one sat back and was like, there's a book? In the book that's based off of, the genders are flipped. So the boy is older and he's the computer hacker, and then the girl is the younger child. And they very specifically reversed that for this movie, so that way it was the girl that was the hacker. And I make a lot of jokes and poke fun at a lot of things in this talk, but that one's actually really cool, especially given the movie came out in '93. It was very neat to see that sort of kind of progressive representation in movies going back that far. And it's kind of scary to look at 2020 when we're still struggling with it a bit, but we should celebrate the places that did get it right. So it's a very cool, neat feature of the movie that you may not have ever seen. All right, Exhibit B, our second movie. Again, a hacker-ish type of theme. And our hacker gets given this system to work on writing a worm. This absolute ergonomic nightmare. Now, don't get me wrong. I'm doing this presentation on a dual monitor setup, and I do have a few extras. But this 7-monitor monstrosity, I don't know what bothers me more, if it's the fact that the screens are different sizes, or if the fact that there's all this gap in between them. I'll give them credit because that little fireball you see does kind of trace between all the monitors, but otherwise looks kind of cool, I guess, if you discount the ergonomic nightmare. We're going to see a picture of that in a second. So as our hacker is proceeding with his worm, he's compiling things. At least I assume this was supposed to be a compile operation because, let's be honest, this doesn't look like anything real, but it's this graphical, and then these boxes fly in as they compile, and this is not what Maven and Make and all of those things look like. But I guess the cool part is when the compilation fails, the thing just explodes on screen and stuff goes flying everywhere and it turns red. And I'm not gonna lie, that's kind of a cool way to break a build, but also spectacularly impractical and a far cry from the scrolling text that we're all used to seeing. So this is our hacker working very diligently in a spectacularly comical montage as he's working on his worm, like we all do, and we get really excited when we're coding something, and we stand up and we lean in, and we've got that kind of fake smile plastered on our face. And I guess I can't harp on him standing up too much, seeing as these monitors are placed in such a way that you'd really kind of hurt yourself looking around. So again, hopefully in chat we've seen the movie come through, and the name of it is Swordfish, released in 2001. This stars Hugh Jackman as a hacker who is recruited by John Travolta to write a worm. I'm going to leave it at that in terms of summary, but believe me, I didn't capture all of the kind of amazing computer representation that you can find. Very fun, popcornish movie. And fun fact about this movie, this came out in 2001. In 2008, Hugh Jackman was voted sexiest man alive. I forget the magazine. I should have looked it up before this talk. I think it was People. And in the movie, this is how they chose to portray him during the montage. And this is really kind of sobering, because if 2008's sexiest man alive, and this is the best we can possibly do to make hacking look attractive, there's no hope for the rest of us. Okay, last movie, Exhibit C. This picture just gets worse the longer you look at it. So going from the outside or the back in, on the right, these are presumably file system outputs. They look kind of cool. The file lists scroll up and down. A security spectacular nightmare that not only is your files very easy to see, they're full on put on display for anyone who may walk in here. And then, as we all know, all IT departments have a giant setup where we have this giant monitor that everybody uses. I don't have a picture of the keyboard, but it's this really super futuristic looking thing where he just kind of taps on the table and it works. And this does the cardinal sin that a lot of these shows and movies do. Echoing the password in plain text is actually not the sin, although it's quite up there. But you'll notice the text field that the password goes into is literally the exact size of the password. Pet peeve of mine that they always seem to fill. This movie does it a few more times. And in this case, it's assuming you're going to have a 3-character password because that's the extent of the form. And I could go on and on about this, but let's keep moving. This, a little bit later in the scene, a hacker has broken in, and this is presumably their storage system. The reason I point out the white sparks that you see, I think you can see my cursor, literal arcing electricity, which is not at all any kind of OSHA violation or any kind of danger or anything like that. But this is what happens when you hack. You cause the servers to emit electricity because it's pulling data so fast, I guess. So here's our hacker during this particular scene, and he's scrolling through the file system. And, you know, I know some people who like to rice their computers and use transparency effects and things like that. So this is slightly less of a stretch. At the same time, absolutely hideous that anyone would contemplate using this as their file browser or as their terminal. And then the last image from this is the most justifiable one out of all of them. So this is him downloading a file. And we know that all files are transmitted in not binary, but equations because reasons. But the reason I say this is the most viable one is that we've all seen those downloads that get to 99% in 2 minutes and then take an extra 5 for that last percent. So arguably speaking, since those percentages end up being kind of useless, it's almost better to have this kind of cool visual effect. And I know I'm stretching, but when you've watched a whole bunch of really bad computer movies preparing for a talk, you kind of pull for anything you can get your hands on. What is the name of this movie? This is Hackers. This is by far my favorite of these corny movies. And this was, the screenshots I took were literally from like a 3-minute segment. The rest of the movie, if you can believe it, gets worse. That said, if you've never seen it, absolutely go see it. Absolutely amazing movie. Released in 95, so you can imagine it took some liberties with where we thought futuristic, computers would be. It's also great because there's this one point where one of the hackers gets a new laptop and they start mentioning some of the specs, which is always funny to hear what was impressive back then. So these are all old-ish movies, and I could have found some more recent examples that were equally as bad, but this got me wondering, if these movies were released in the early 90s, all the way up to the early 2000s, what would they look like today? What would they look like in today's technology stack? And I know some of these use things like modems. That Hackers one was him dialing into somewhere, and they had the old CRT monitors. But from a technology standpoint, what would things look like today? So before we go on to the demos, I want to talk a bit about some of the background technologies that I'm going to use. And we're going to see a few more things during the demos themselves, but there's a few basic concepts I want to make sure everyone understands because they play into both demos, and it's a relevant underpinning to this entire rest of the talk. So the first is containers. Containers has really come around as a popular technology these days. If you've never used them, it's effectively a way of packaging the entire runtime for an application into an image. This image is then run as a container directly on your system. So if you're relating this to virtual machines, you're not too far off, but instead of having a hypervisor running in this entire fat virtualization layer, a container runs directly as a process on top of your system itself. It means whereas we previously would talk about VMs in the scale of a couple, maybe a dozen, we're now talking hundreds of containers because they are so lightweight. They are very easy to just destroy and re-stand up. And again, you have these isolated environments because it's completely encapsulated inside of these images. So we get away from this whole it worked on my machine type of thing that developers are known for, because all of those libraries and all of those dependencies are packaged inside the image. And then the image is what's shipped around between development machines, between promotions from development to QA to prod and so forth. Now, to run your containers, you can just run them directly on your system, but that's ultimately not going to scale. Part of the benefit of being able to spin up so many containers and this idea of if I can take these very small containers, now my architecture looks different too. We have this microservice concept where my previous monolith application, which was very slow moving, very hard to deploy, is now broken down into a number of smaller containers, each which have their own release cycles, they have their own bug fix cadence, and you can you can upgrade them independently. But doing all of that would require a lot of manual work. How do I take my container and get it out to a machine? Or how do I get it to multiple machines? How do I make sure it stays running? If that container dies for whatever reason, I'm going to want someone beside me getting the 2 a.m. text message that the service is down. I'm going to want someone else keeping an eye on it, making sure it's running. So these days, instead of just running containers on your own, a lot of enterprises are using an orchestration engine. Kubernetes is a very popular upstream orchestration engine. It provides things like scheduling, all of the replicas, so I can say I want you to scale my containers up from 5 to 20. And it'll also keep them alive. So if my container dies, Kubernetes will take care of restarting it. OpenShift is Red Hat's enterprise Kubernetes distribution, which builds on top of that with developer tooling and a UI and a whole series of other features around making it more usable and enhancing it beyond just that simple orchestration layer. Now, for the next 2 demos, we're going to see some applications running on top of OpenShift, and I'm going to explain what those are in a second. But for now, I just want you to have an idea of those 2 concepts. That we have containers and what they bring to the table, and we're going to be spawning containers for the rest of the talk. And then they are running on top of an orchestration engine. In this case, we're going to be using OpenShift. So like I said during the intro, I had this idea of how do we take some of these old movie scenes and modernize them with today's technology. So I decided to focus on war games, the oldest and second favorite of my movies. This came out in 1983. This is where we are going to get into some spoiler territory. So again, sorry, but it's been quite a bit of time since that movie's been out. Stars Matthew Broderick as David Lightman, an aspiring hacker who just wants to play video games. And he searches around for different systems that he can attempt to find. He finds one and logs in and starts playing some games. And of course, it turns out to be a military system, and that ends up triggering a whole bunch of problems for David. We'll talk a bit more about that because there are 2 particular scenes that I want to dive into. The first is going to be a dev-focused type of demonstration. So we're going to focus a little more on the actual coding, the implementation, the architecture of what these applications would look like today. So let's talk about the scene itself. This is fairly early in the movie. David goes to school and he leaves a war dialer running on his computer. You'll notice in the middle there the absolutely amazing modem that he's got going on with the phone sitting on top of it. Anyone who's watching this that was born in the last 20 years has probably no idea what that is. I am, I guess I hate to say this, old enough where I've actually seen one of those. My dad had one in the house. Kind of scary to look back, but let's look forward. So he leaves this running, and it is going through and dialing all numbers within a particular area code. And the computer is logging for him which ones actually connect to a computer versus which ones are just some person answering their phone and getting the ear-piercing modem screams that, again, you younger generation has never heard before. Trust me, very cool. So he leaves this thing running and it sequentially goes through them, and it spends all day for him as he's at school, and he comes home and gets to see the report. So what would that look like today? So let's do a slightly modified version of it. So instead of just saying, I want to loop from 555 all zeros all the way onward, we're going to set up a message bus. It's going to be running in RabbitMQ, and it's going to have an entry for each one of those phone numbers that we want to test. Then we have a container, this fake Whopper dialer, and it's going to go and it's going to pop a number off, and it's going to simulate as if it's seeing it's live. And then jump the results to the results queue. And all it's going to do is randomly say it connected or it didn't connect. That output isn't so important as much as the fact that we're getting output. Obviously, it's not dialing a phone number, especially since they're 555s. I could have modified this to have IP addresses and say we were hacking something, but the point is really the architecture here, and I want it to stay fairly close to the source material. So that Whopper dialer is going to be running as a container inside of OpenShift. And then this little human down here is going to be a listener that I have on this results queue that's going to run inside my terminal. So let's take a look at that now. On the right, in fact, before we get to that, let's look at OpenShift. So if you've never seen it, the crash course for OpenShift is that this is the developer view. This represents a single container that's running inside of it, and that container is running RabbitMQ. Now I set this up ahead of time because getting this deployed isn't a terribly interesting part. What is interesting is the fact that I'm not going to have RabbitMQ running on my machine. I just want to use the one deployed in OpenShift, which is running in a cloud somewhere that is ultimately irrelevant for my purposes. I know I have a login to OpenShift. I know I can connect to it, but where it actually runs from a developer standpoint, it's kind of cool that I don't really have to care. But like I said, I want to be able to take advantage of the fact that it has Rabbit running. So I'm going to set up a port forward. So this is going from my machine. It's going to forward 5672, the typical Rabbit port. And it's going to forward that directly to the RabbitMQ container that you saw running inside of OpenShift itself. And we're going to run this populate command. What this is going to do is just dump all the numbers 555, 4 zeros up to 4 nines into that message queue. So if nothing else, I'm showing you that the port forwarding is working. And we'll set up that listener. Now remember, this is us here that is paying attention to that results queue. And it's going to keep an eye for whenever a result is added. So we have our queue in place. We have our data that we're going to test. We have our listener ready to receive the results from the outbound results queue. Now let's deploy our actual dialer itself. So I use the OC command. I don't think I said this before, but OC is the OpenShift command line client, very similar to kubectl if you've ever used that before. And what I did was say, use this image that I've created, this Whopper dialer image, and I want you to go and deploy that inside of OpenShift. We can see here we have a new entry. The light blue means it hasn't yet started. It's likely just pulling that image down from Docker Hub or Quay.io. I honestly forget at this point where I have that one located. I think it's Docker Hub. And it's going to start up that container for us. Now, once that container creates, like I said, its whole job is to look at the phone numbers queue, take a number out of that queue, pretend it's going to dial it, so it's going to wait a couple of seconds, and then spit out a result to the results queue of either no connection or it's going to randomly say connected. And we can see it's taking place. So that container is running, it's starting to pull numbers off, and it is spectacularly slow. That's okay though, because part of what we want to see here is how these cloud native architectures give us the ability to speed this up. So we go back to my slides. Right now we have a single Whopper dialer that's pulling numbers out of the queue. What if we had 10? Let's say we wanted 10 instances of my application running so it can pull effectively 10 at a time and produce those results. And if you've never done this before, this sounds like it could be kind of difficult. All I'm going to do here is go into OpenShift and click. I didn't count when I did that, so we're going to say close to 10. I clicked a little too fast. And you can see everything kind of spinning up here as OpenShift spawns off new containers. So the same image, but it's now creating 2 up to 5, and it's ultimately going to have 10 of these containers running concurrently. If we go back to the output, you should notice it's a little bit faster, because instead of the single thread model, instead of the single application model, we've put that scaling into OpenShift itself and into our orchestration engine. And we've designed things in such a way that instead of using a loop where we had one process that was kept track of the numbers, we stuck them into a message queue and we let us just pop numbers off whenever this worker node was ready. And that's kind of cool. But you know what's cooler than 10? Because this is still going a bit slower than I wanted. How about 50? So I'm going to say edit count. Does the same thing. I'm simply showing you alternatives inside of the UI. And quite frankly, I don't feel like clicking that up switch 40 more times. But the initial demo of that makes it look kind of cool. We can see, boom, we already have 50 pods running. And now we're starting to flow through the numbers. You get that visual kind of confirmation that, yeah, all of these extra containers are really putting in the work here. Cool, but can we go further? How about if we edit it through the CLI? So again, doing the same thing I could do through the web console, just showing you a different alternative. And I'm going to go down, and what this is doing is editing the resource description that represents that running application. So the Whopper dialer as an application. And what previously said, I want 50 replicas. Let's take 100 of them. So I've just told OpenShift, you know what? I want you to take my application and I want you to scale it from 50 up to 100 nodes. And effectively, if it wasn't for my rambling, we would have started at one single instance of my application and immediately scaled it up to 100. Now the numbers are flying in. Our architecture is cruising that we were able to very simply scale it up to facilitate the extra load that we wanted. Just as some proof from the console itself, I'm going to do a get pods, and we're going to grab just the running ones. Excuse me. We do a count. We see 101, which isn't a surprise because that extra one is the RabbitMQ container itself. And then I can very easily go back in and scale things back down. So let's say that we've passed some kind of threshold where, we threw extra resources at a particular problem, or we wanted to scale this up to handle inbound load that spiked for whatever reason. We can very easily scale things back down. And it's a little bit hard to see on the side because of the back off, but we look back into the UI and we see that there's only 5 pods. And we can see if I hover over it, that dark blue line, that 95 terminating is OpenShift canceling, or I should say killing off. Well, probably not the best choice of words, but killing off 95 of those pods to bring us down to 5 running ones. Now I said pods, that's the Kubernetes term for a container. Not exactly one-to-one, but if you're new to everything, just associate them together. That when I use pods, I effectively mean interchangeably with containers. And we're now back down to 5 running containers, which is very clearly evidenced by the fact that we only have a few connections slowly trickling in. Now, one thing I had forgotten to do is I did have a slide before I flipped to 50 to show, we're going to scale things up significantly, but that's okay. We saw it during the demo. Now, what are our lessons learned? What did that demo show us? On one hand, we saw what happens when you take the development environment off of your local machine. Now, instead of telling your new developers to the project, all right, download Rabbit and download Mongo and download this piece and that piece and get them all running and configured so that way you can run your application, let's leave that. Let's leave that off to the cluster, which is where it's ultimately going to run anyway in production. And let's leave it to a similar cluster, potentially a development cluster. And we can use that port forwarding to make them appear as if they're running directly on our machine. So that gives us all of our local development type of flow, but we don't need to have developers stand up these massive environments on their own. We designed this application for scalability. This would have been dirt simple to write as a simple for loop from 4 zeros up to 4 nines and try that. But we wouldn't get anything out of it. If we scale it up, that loop would execute from the beginning again. And now we would double test 0, 0, 0, 0, and so forth. But if you design things with a cloud native approach in mind, and you understand that having containers and microservices and an orchestration engine in play, you could put a lot of that scalability off to the orchestration engine. So we designed it using a message queue and nothing terribly difficult from a code standpoint. But now it allows us to independently scale up based on our needs. And you saw that scaling went from 1 up to 100 and then back down to 5. And to that point, we're going to let someone else handle that for us. If you've ever scaled a more traditional app, or if you have a fat monolith that you're stuck working on for legacy reasons, you know that scaling can probably be pretty difficult. But if you design ahead of time, then you can push that off to some other application. Leave your code running the way you want it, and then you have OpenShift. You have your orchestration engine come in and let it control the scaling for you. So for our second demo, I'm going to focus a little more on the ops side of things. So again, let's discuss the scene that we're talking about. Now this takes place at the end of the movie. Whopper, the name of this computer that the military has created and put in charge of all of their weapons, has decided that Russia is attacking and it needs to annihilate them. So David Lightman and the original systems creator, Dr. Falcon, realize that you can get the computer to learn that playing tic-tac-toe is a pointless game because nobody wins. And then they set the computer to play itself, and over time it started spinning faster and faster and presumably getting frustrated as much as a computer can get frustrated. But starts realizing that you can't win tic-tac-toe. And once it overloads, it inexplicably blows up into smoke and sparks, which is, I guess, what happens in data centers under high load. I've never been that level of admin, but that's fine. So in other words, they've overloaded the system. They have it playing too many games of tic-tac-toe, and it overloads to the point of cheesy 1980s sparks. So we're going to simulate that. First thing I want to show you is a small application I developed. The left two columns are the two worker nodes in this cluster. So very brief breakdown of OpenShift architecture is that it has a set of master nodes that are HA available control plane, and then worker nodes where we have our actual workloads running. And then on the right is just a track of pods or, again, containers that we are attempting to schedule but are unable to. So the bottom two panes, don't worry about those. Those are just supporting that site, which is running locally, connecting to the control plane and just getting status out of Kubernetes. So we are going to do exactly what they did in the movie, and we're going to crash the system. So you'll see I run the script, and I'm not going to lie to you, it's very, very intimidating running a script literally called crash during a presentation. Thankfully, this is recorded, so if something goes horribly wrong, you're not going to know, but live, it's a little intimidating when you see crash. What crash does is start a series of pods, and it allocates a ton of memory to each of them. So big that it's going to overload what can possibly fit on these nodes. And these are pretty beefy nodes that we get by default with our internal installations. But the point stands. The left two, we have our fat tic-tac-toe games, which is an extremely well-programmed loop that, not even a loop, it's bash call to sleep for like 10 minutes, and then the container ends, but I should be done with this in 10 minutes. So these long-running processes that have a lot of resources dedicated to them, they've filled up the worker nodes, and we are unable to actually do any more work on it. So those pending requests will stay in unscheduled until something becomes available. But for the purposes of the demo, and what we're looking for in emulating this war games scenario is that we were able to overload the cluster and it can't take on new workloads. And if for some reason an OpenShift cluster was ever responsible for targeting systems for the military, this would be one way of breaking it, that we could overload the system and all those targeting things wouldn't be able to get scheduled and wouldn't run. In case it's not obvious, I've never really worked in the military, so I don't know how things work, but we'll run with that. So I'm just doing a quick cleanup, just kind of deleting everything back to a state, but in this case, the heroes have won. We've managed to take down Whopper before it fired the missiles, and we managed to take down our entire cluster in the process. So how could we have prevented that? We are the IT admins for Whopper. We don't like the idea that our system could be taken down by tic-tac-toe. I feel very confident saying that. I can't imagine there's not a lot of ops people out there saying, no, I'm perfectly cool with that setup. So how could we have prevented this? So let's start with the less interesting but extremely useful approach here. We're going to put a quota on memory allocations. So this is on a per project basis. And I'm saying that within this particular OpenShift project, you can only allocate X amount of memory for deploying pods. So we can see now, I believe the math works out that after 4 of them, we will have taken up enough memory to trip the quota. And we can see here that we're getting this error message. We're saying that you've fulfilled the 32 gigs of memory we've allocated for this project. If we look, we see the 4 of them running, 8 gigs apiece, so math works out there, but the requests start to get pushed back to the project. This will allow other projects to continue working, which is great unless you're in the situation where the other projects are trying to cause the end of the world by nuking Russia, in which case it's probably not so great. But point still being, we have won. We have, we as the admins have won. We let Whopper function correctly, and we are not letting the users destroy it with simple tic-tac-toe games. So we're going to clean those images up, and it takes a couple of seconds, mostly because of how spectacularly lazy I was when writing these fat pods and trying to interrupt that sleep and then destroy things. It'll take a bit to clean up. The next approach we're going to do, though, is way cooler. Not necessarily more practical, but definitely from a cool standpoint. Now in OpenShift, all of our worker nodes are controlled by OpenShift itself. And that goes all the way down to the level of provisioning them. So what if we told OpenShift, if you run out of space and you need to allocate more resources, you can do it yourself. So we'll delete that quota because that's going to stop this demo out the gate. And we're going to apply an autoscaler. Now this is going to take a bit, so I will show you the actual contents of this and explain what it's doing in a second. But for now, we're going to run crash. We're going to give us some room here, and I'm going to watch on. Now this call, as I recenter things, is going to show us that we have, again, our 3 master nodes, this HA control plane, and we have two worker nodes currently running. Some of you may have picked up by now why I'm running this in AP Southeast. I have no idea. I didn't pay attention when I requested this system from our internal provisioner, and this is what I got. And at this point, I'm kind of more intrigued to see if I can run with it because I'm based out of New Jersey, so this is almost as geographically far as humanly possible. So, during that talk, you'll notice we went from 2 running machines to a 3rd machine, this provisioning and provisioned state. What happened is this autoscaler, I'll close this out for a second to show you the autoscaler. I have set it up to say that for this particular region, I want you to be able to scale up. So it's 2 resources that I just create inside of OpenShift. You saw me run the one OC command. Now what's going to happen is when OpenShift gets a request and runs out of space, if we go back, we're at the same situation we saw earlier where the unscheduled pods are still hanging around and we can't fulfill them because we just don't have the resources available. We've configured OpenShift and we said, no, I'm going to give you some room to grow. And here's the specification for how to grow and how far you can and what's going to trigger it. And the details of the real nitty-gritty details are outside the scope of this talk. But we can see, though, that OpenShift has begun this process of provisioning. And what it's doing is it's standing up a new instance in the cloud. It's going to initialize that with Red Hat Core OS, which is going to be a container-driven, a container-optimized version of the operating system. And it's going to take all of the pieces necessary to register it with OpenShift itself, so that way it can act as a worker node.
Wibbly wobbly, timey-wimey stuff.
Okay, so after some movie magic time jump here, you can see that our node has started. It's registered itself with OpenShift, and it's getting to the point where it's going to start receiving workloads. We should see in the very near future, OpenShift is going to take those unscheduled pods and start to deploy them over to this 3rd worker node that got stood up as a result of this process. So 2 different approaches to accommodate user load. We have the idea of quotas, where we can prevent users from deploying more than they're supposed to. And that makes sense. And realistically, that's the better option here. But the cooler option is if Whopper was able to scale itself up and be able to handle the extra loads that the tic-tac-toe spam or the tic-tac-toe fat pods were giving it, be able to spawn up some new resources and continue to field new requests. We see that our pending pods have bumped over from unscheduled and then are running on our new node. Thankfully, right as I say that, they all flip over to green and they're running. So another way for Whopper to be resilient, if we didn't set the quotas on the project, or we had it in place that we're accepting of some threshold where it spawns its own resources, then we can do some really cool things where OpenShift decides, you know what, I need more power, so I'm going to go and provision my own full-blown VM. I'm going to attach it to the system as a worker node, and it's just going to start fielding requests just like any other machine. So to finishing up, what did we learn here? Again, the safer answer, the better approach is, as an ops, as an administrator, you probably want to keep an eye on project and user quotas. I come from a development background myself, and I know that if you give me the space and resources, I will use them. So it's always a good idea to have your project and your user quotas in place. Now, I didn't show the specific details, but this one was memory-based, and you saw it in that error message. There are a lot of other ways to define quotas. And then the other piece that automation is really the way of the world right now. We see it in CI/CD systems. We see it in a number of other places. Here we see it that we've configured OpenShift to be able to automate repairing itself and automate certain operations that would have previously required ops to come in and say, I'm going to allocate some new resources. And depending on your setup, that may be pretty heavyweight for ops to do. If they have to manually provision the machine, if they have to do any kind of steps of connecting it to OpenShift on their own. You know, if you're not using something to automate that for you, that could be particularly painful. And even if you have something in place like Ansible that will do some of that automation, the more the better. And if we can have OpenShift take care of all of that, things get even better for us. So with that, I want to thank you. Again, this talk is really designed to be done in person. So thank you for bearing with me as I kind of adjust to this virtual world. But it's especially weird being recorded because I want to say thank you for being vocal in chats. I'm hoping we all had some fun with that. And I'm hoping that chat was even an option, or as compared to me just saying it in this talk as a possibility. You can find me on GitHub and Twitter, both of those at JDob. That's the best way to reach me. And with that, I'm going to say thank you and enjoy the rest of the conference.